So we were talking about dimensions last time. And I mentioned that a ring R is semi-simple. So I mentioned that there was a classification of these rings. Well, you know that R is the direct sum of its minimal ideals, because whenever you have an ideal, you can just split this R as that ideal plus a complementary ideal. And, well, you use that to split every such ideal. So R is a direct sum of its minimal ideals, and it turns out that R is a direct sum of division algebras, of endomorphism rings of division algebras. Ti is a division ring. So this requires some work, but it's not so hard. The whole point is that R is Noetherian. So being semi-simple implies that it's Noetherian. And what we've seen already is that if R is semi-simple, then, well, this implies that every module, every R module, is projective. And if every R module is projective, of course, this is going to happen as well. Every R module is injective. So this we also proved. That was an if and only if. And what we didn't prove is this statement. So now that we know that R is semi-simple implies that it's Noetherian, then this implies that, well, R is Noetherian, and every module is flat. Our module is flat. Now, of course, this implies this. So if it's semi-simple, then it is Noetherian. And if every module is projective, then in particular, they're flat. But the important implication is the other way around, that if you are Noetherian and every module is flat, then your ring is semi-simple. And that's not hard, because if you have an ideal in R, then R over I is flat, well, just because it's an R module, but it's flat, it's finally generated. On a Noetherian ring. So we've seen that finitely presented modules are projective. So in particular, finitely generated flat modules, finitely presented flat modules are projective. So finitely generated flat modules over a Noetherian ring are projective. But if R mod I is projective, then this surjection here splits. And that means that this I is a direct summand of R, which is what we wanted to prove for R being semi-simple. Okay, so that's a criterion of being semi-simple. And of course, all of this is equivalent. Well, notice that in particular, R is of global dimension 0. Every module is projective. Okay, so I'll just make a couple of comments. I'm not going to comment over the whole section there. But here's another definition. A ring R is quasi-Frobenius if R is injective as an R module. As an R module. And here I need to be careful both on the left and on the right. So in other words, the injective dimension, both left and right injective dimension of R is 0. Injective dimension. And here both left or right. Remember that for injective or projective dimension, I needed to be careful whether or not it was left modulus or right R modulus, and this guy is both, is 0. So of course, a semisimple ring would satisfy this condition, because every module is injective. In particular, R is injective. So a semisimple ring is quasi-Frobenius. So endomorphism algebras of division algebras are quasi-Frobenius. This guy's endomorphisms algebras over division algebras. So if you think about this, if they are, so think of it as over a field. So these are just the direct sum of matrix algebras, just matrices, n by n matrices, and take sums of those. So matrices by blocks. There's a property of this. These are finite dimensional. You have a trace, and the trace is non-degenerate. So, in other words, the ring itself is isomorphic to its dual. So that'll take us a general definition. And for this, I need a field. Let K be a field. And R be a ring over that field, a K algebra. Then R is Frobenius if it's isomorphic to its dual. As R modules. This is over K. So in particular, R needs to be a finite dimensional K algebra to even have this isomorphism. Okay, so I claim that a Frobenius algebra is quasi-Frobenius. So I need to prove that R is injective. And if I have this isomorphism, then I'm going to use that this guy is always injective. So RK. Okay, so that's a dual of R as an R module. It's always injective. We've already done this, but I'll repeat it. Remember, we have this natural isomorphisms. Tensor N. Okay. It's naturally isomorphic to M. N. Okay. Let me just use this. Let me be careful on where I want to consider these guys. So to see which one is the one that I want to move to the other side. So if I consider M as a right R module here and N is a left R module, and this is just a morphism of abelian groups. So this is just an abelian group, and I can just only take morphisms of abelian groups here. Then this is now a right arm module, and here I'm going to take this n was a left arm module. K is an abelian group, so this hom here of abelian groups is now a right arm module, and I can look at the category of R modules here. But this is a right arm module, so I should write as mod R. And we've done this by looking at, and this is an adjunction. These are adjunct functors. So here the functor is tensoring by n, and here the functor is hom from n into. So this is applied to m, and that one is applied to k. So I'm going to take the case where n is the ring R itself. And what we see is that hom for abelian groups of something tensor over R with n something, this is the same thing. Well, tensoring by R in this case, so this is R, n is R. It's just the same thing as taking hom for abelian groups of dot by itself. Let me hold now, let's put names. So this is M, and this is my K, and this is just M. Okay, but this is the same thing as hom in the category of R modules from M to hom in the category of abelian groups R. Okay. So that's the adjunction we have. That on one side, I look at the functor is just the identity functor. It takes M to itself, but it forgets the R module structure, and it only remembers the abelian group structure. I'm taking hom in the category of abelian groups. And on the other side, I have this other funny functor that it looks like the dual. It homs from R into an arbitrary abelian group. Okay, so what happens is that if R is also a K-algebra, remember this is all the case where I have n and is a K-algebra, then all these abelian groups actually are vector spaces. All the morphisms between, I can take this K to be a vector space now instead of an arbitrary abelian group. And this is always a vector space, so the morphisms, I can take them in vector spaces. And the same thing here. If I take K to be a vector space over K, over little k, then these homs, I can take them as K-linear maps, and this is a vector space. So if R is a K-algebra, and I restrict to K being a vector space over K instead of just arbitrary abelian groups, then what I get is this adjunction, that is K-linear morphisms from M. K is naturally isomorphic. Well, M and anything, I'm going to do this. This is the same thing as hom. Now, in the category of R modules, mod R between M and hom R. And now this is K morphisms. K. And here, yeah, so this is K. Okay. So on this side, the functor is from abelian groups. I'm sorry, from R modules to K vector spaces. The functor is just leave it itself and forget the R module structure. And on this other side is take the dual. Okay, so okay, so in particular, this guy here is that functor applied to R K is this functor applied to K in that vector space. So this is a right adjoint to this functor, which is a functor that just forgets the R module structure and only remembers the vector space structure. And since this is a right adjoint functor, so it's right adjoint, so it preserves injections. It's right adjoint, but it's right adjoint to an exact functor. To an exact functor. And this is the only thing that is important. I think I've proved this before. If you have a functor, if you have a right adjoint functor, then it preserves injections. But it doesn't really preserve injectives. It just preserves injections. However, if it's right adjoint to a functor that is itself exact, then it preserves also injective objects. And this functor here that just grabs M, forgets the R module structure, and remembers the vector space structure, is clearly exact. So this is right adjoint to an exact functor, therefore it preserves injectives. And K itself is injective. Being a field, K itself is injective. Since K is injective, then K, R, K is injective. But then in the category of R modules, okay, so this guy is injective, and if I have this isomorphism, then R is injective as an R module. So being Frobenius is in particular quasi-Frobenius. And of course, being semi-simple is in particular being quasi-Frobenius. Now, we always have this thing that you have a map from R to like this. You always have this non-degenerate pairing. This is over K to K, which grabs some phi here, tensor, an element in R, and you just send it to phi of R. So when you have this isomorphism here, you're saying that pairing is actually non-degenerate. So this gives you a map from this guy to the dual of R. Which we're exposing here to be non-degenerate. So on a Frobenius algebra, we have, therefore, a map from R tensor R into K. Because this R is isomorphic to that, and then I just compose with its evaluation map. Hom R K tensor R. This is the evaluation map that we have here. And here I'm using the isomorphism that the Frobenius algebra structure gives me. Okay. So Frobenius algebras come with this non-degenerate pairing on itself. You just map to the duo by the Frobenius isomorphism, and then you get back to your field by just the evaluation. So we expect to see this kind of structure on matrix algebras, as I said, because every semi-simple algebra is a direct sum of matrix algebras, and matrix algebras are in particular Frobenius. So what is the structure for matrix algebras? Okay, so when R is the endomorphism or a direct sum, it doesn't matter. So if R is the endomorphism algebra of some vector space, everything was over a K, over a field K this time. It wasn't just an arbitrary endomorphism of a division algebra. Of some finite dimensional vector space V. What is this map? Okay, so I need to find an isomorphism between R and Hom RK, which is this isomorphism here that a Frobenius algebra should give. So I need to give you a map between the endomorphism ring of a finite dimensional vector space and Hom from that endomorphism ring into that vector space. Can anyone give me that map? So what is the isomorphism between the endomorphism of this guy as a ring, well, as a module over itself, and Hom K between that endomorphism ring and K? So what I need to give you is, for any matrix, I need to give you a map from matrices into the field. And that's very simple to construct. So if you give me a matrix T, so this is an endomorphism of the vector space V, you want to get another map that grabs an endomorphism of the vector space V, and it gives you a number. So this map is going to be from S, and, well, this is the only thing that I can think of. And take the trace. So check that, well, I might have screwed up and I needed to take the trace of S times T. Luckily, for this algebra, it doesn't matter if I take S times T or T times S. The trace is the same. Just to see whether or not the structure that you get is right R. So if I, remember, this should be an isomorphism of right R modules. So for that, I need to look at here as the left R module structure of this guy. Okay, in any case, the trace is symmetric, and this gives you, this is an isomorphism. Why is that an isomorphism? Well, if this, let's look at the kernel of this map. So something is in the kernel of this map if the trace of T times anything is 0, and that's easy to check that this implies that T itself has to be 0. If you have a matrix that you trace it with absolutely anything is 0, then your original matrix is 0. That's easy to check because you can pick point by S, just pick a basis of V if you want, and you can just pick each one of the entries of T as a unique non-vanishing entry in that diagonal by just multiplication. So the kernel of that map is 0, and both spaces have clearly the same dimension, which is just the dimension of V squared. All right, so that's isomorphic. And, well, if you trace this here, then it should give you an isomorphism, a bilinear form in endomorphisms of V. So now, this should correspond to a map like this into the field. And it's clear what that map is. If you give me two endomorphisms, I'm giving you back the trace of the product. So that's this map here. And the same holds for direct sums of such algebras. And essentially, these are all Frobenius algebras that I'm going to care about. Well, these are all semi-simple. So let's look for some non-trivial Frobenius algebras. Okay. And this is a non-degenerate pairing. So that's one example. So the other example is G being a finite group, and K being a field, an arbitrary field. Then the group algebra of G is a Frobenius algebra. So the group algebra of a finite group is isomorphic to its dual. Now, I mean, of course, when the field says of characteristic 0, then this guy is semi-simple. And then, therefore, it's Frobenius. But this holds for an arbitrary field. So in particular, if the characteristic of the field divides the order of the group, this guy is not semi-simple. And that's easy to check. Just for a cyclic group with p elements, you can construct a non-trivial extension of modules. So that's an exercise. Check. And this is an explicit check that there are non-trivial extensions of Z mod P modules, Z mod PZ, by Z mod PZ. So I'm going to call it like this. Z mod PZ as Z mod PZ modules. So this is to check that well, I guess instead of Z mod PZ, I should have done this over FQ. There are non-trivial extensions of the group algebra, of the group, which is the cyclic group with p elements, over Fp. So you can just take the standard representation of that group, and there's a non-trivial extension of that guy by itself. So the group algebra of this guy cannot, over Fp, cannot be semi-simple. Okay, but still, this guy is Frobenius. And the statement here is that we constructed this in two different ways. So one way of thinking about that algebra was looking at this with the multiplication being something like this. So this guy was given as a vector space whose bases were these symbols. And that's the multiplication of that vector space given this. Or we looked at this generically as the space of functions from G into K. Okay. With the multiplication being the multiplication was the convolution. So if you give me two functions, f and g, this g has nothing to do with this g. Applied to an element A in the group, this was written as 1 over g, the sum of f of, A times y inverse, g of y, where, so that's it, over y into So now, these two are isomorphic. And that's this isomorphism that gives you that this guy is Frobenius. And that isomorphic was very, very explicit. The isomorphism was that we would send this function, the function that is the characteristic function, f, which is the characteristic function of an element g, we would send it to EG. And we checked that this was an isomorphism. So that's the isomorphism of K of G with its dual, because it's clear that this guy is naturally isomorphic as to the dual, as a vector space, is naturally isomorphic to the dual of that guy, where you just send G to the characteristic function of G, or just the coefficient. Right? So these are functions on G. Therefore, these are functions, if you extend this linearly, it's functions on this space. Linear homomorphisms from K of G to K. So that's a quasi-isomorphism, the isomorphism of this guy with its dual. And that's why this guy is Frobenius. All right. So that's examples of Frobenius algebras. What else do I want to say about Frobenius algebras? Okay, so if the ring R is quasi-Frobenius, namely if R itself is injective, then, well, the injective dimension of R is 0, clearly. But then every projective module is injective. And every injective module is projective. Now, of course, if every projective module is injective, then in particular R is injective because R is projective, and then that implies that that R is quasi-Frobenius. That was the condition of being quasi-Frobenius. But now, if R is injective, then you can prove quickly that every projective module is injective. Because every projective module is a direct sum of a free module. And free modules are now obviously injectives, because free modules are just R to some power, and that's an injective to some power that is still injective. And then a direct sum is going to be injective. So this is isomorphic. If and only if this is easy, and that these two are isomorphic, that's also easy. So Frobenius algebras have this property, which is weaker than being semi-simple. Well, we already have an example of something that is not semi-simple. So it's weaker than every module is projective or every module is injective. Just those that happen to be projective are also injective, and those that happen to be injective are also projective. Okay, so those are Frobenius algebras. I think eventually I'll talk about Calabi-Yau algebras. So I mentioned the other day that if you have a Lie algebra, then you can cook up a universal, an associative algebra that very much likes to be Frobenius, very much likes to be semi-simple, but it's not, because I have non-trivial extensions, just that I need to look at infinite dimensional extensions of modules over that. So this guy does not have, therefore, an isomorphism to its dual as U of G modules, but it does have a derived isomorphism. So this guy does not have, so if I call this guy R does not have an isomorphism between R being isomorphic to Hom Rk and this Lie algebra always is over a field, so this is always a K algebra. So this is not true. Equivalently, this is not true, that you have a non-degenerate pairing like this. However, what you can have is you can shift this by some dimension. And now, well, this is a ring, and this is a ring shifted by D. I need to tell you what this is. Or this is an R module, and this is an R module shifted by D. Well, so to even compare these two, I need to go to complexes of R modules. So this is a complex of R module that sits in only one degree, which is degree minus D. And this is an R module that sits in a different degree. And these are a quasi-isomorphism. And the same thing here. Well, I do not have a non-degenerate pairing like this, but I do have something like this. And here D is some number, which happens to be the dimension of your Lie algebra G. So K algebras that have this property are called Calabi-Yau algebras. And they're called like that because the algebra of functions on a Calabi-Yau manifold does satisfy this property. A volume form, a holomorphic volume form on a complex manifold gives you such a thing. And that such a thing is integration. So this non-degenerate pairing is integration against that form. If you give me two functions on two holomorphic functions on a complex manifold with a global holomorphic non-vanishing global holomorphic volume form, then you can just multiply them and integrate it against your volume form. And that's that non-degenerate pairing. All right. So that's why the name Calabi-Yau. And I'll talk about those algebras later on when I talk about quasi-isomorphisms. Let's continue with dimension a little bit, which is what I needed to do today. What else do I need to do today? I think the following. So let's suppose now that I have a morphism of rings. So I have a ring and I have an R algebra. So this is a morphism of rings. And I have a module M, which is an S module. Okay, then, well, I can view M as an R module itself. Okay. So now the claim is that the projective dimension, and this now depends on which ring I take. So if I look at M and I view it as a module over R, or I look at M and I view it as a module over S, there's a relation between these dimensions. So if I take any projective resolution of M over S, M is an S module. If I look at, and when I write S module, I'm writing this as left module, but it doesn't matter. It could be a right module. And then this is going to be right projective dimension, or this is going to be right projective S dimension. It doesn't matter. But the point is that if I have a projective module over S, it's not necessarily a projective module over R. So it's not true that any projective resolution over M, when I pull it back and I view it as an R module, is going to give you a resolution over R. So it's not immediately obvious how to compare these dimensions. What I do know is that I get a bound by adding the dimension of S itself. So I can look at the projective dimension of S as an R module. And this is always bigger or equal than that. So let's prove that statement. And again, what's the relation between projective dimensions and the usual notions of dimensions we have? So let me say this instead of going. So the typical definition of dimension that we study for commutative Noetherian rings, for example, when you do algebraic geometry, is you look at the injective dimension of your ring. So that's called the Krull dimension of your ring. So when you study algebraic geometry, one of the very first things they tell you is, well, how many subvarieties you need to cut off from your ring to get to a point. And that corresponds to the injective dimension of your ring, or the cruel dimension of your ring. So what this is telling you is something different, is if I have a module on a subvariety, and I want to view it inside of this variety, right? So suppose that this is a surjection. When you take spectra, you're going to get an injection of the spectrum of S inside of the spectrum of R. Or you can do the other way around and think of this as an injection. So geometrically, you're going to get a projection from the spectrum of this to the spectrum of R. But whatever it is, you have a bundle over S, or you have a sheaf over S that you want to resolve by vector bundles. How many vector bundles do you need to resolve them over R? Okay, so let's prove this. How do I going to prove this? Okay, I'm going to need a lemma that I think I avoided to prove before, but I don't remember if I proved this. I think I avoided to prove it before, but now I will need it. So let's prove it. The statement is this. If you have a short exact sequence like this, let's say M mapping to E. So it's an extension of M by N. And you have projective resolutions of these guys. So this is a projective resolution of N, and here you have a projective resolution of M. Then this lifts to, well, this is what I have, and in orange is what I want. So this exists. Such that each column is exact and each row is exact. So this is a projective resolution, and moreover, so there exists this P prime I, which is a resolution of E. Such that P10 to P bar to P prime to P to 0 is exact. And remember that, of course, if a sequence, an exact sequence of projectives that is also a projective object. So if it is a projective in the category of complex, then this was split exact. So I'd expect this to be split. So that tells me already how to construct this P prime. So let's prove that that exists. And since we already expect this to be split, then let's just take P prime to be the sum. So I'll take P prime I to be the direct sum. To be P bar I plus Pi. And I want to prove that those actually do fit like this. So I need to construct the maps between them. Those are going to be these guys, and I need to construct these maps. Okay, so we start like here. We started with this situation. And I have P bar 0 here. So let's look at the kernel of that guy so that I stop there. And I have here P0. Let's look at the kernel of that guy and let's stop there. Now, this is a surjection because this sequence is exact. And this guy is projective. And this is a surjection. So since this is a surjection and this is a projective guy, then I get a lifting here. Because this P0 is projective. Okay, so now I have a map from this guy to E, and I have a map from this guy to E, which is the composition of these two. Therefore, I get a map from the coproduct to that, to E. So I get a map from P bar 0 plus P0 to E. This is what I call P prime 0. Okay. So now let's look at the kernel of this. And this is going to be K prime 0. And of course, since this is the direct sum, then this guy is exact. This is just the inclusion into this term, and this is just the projection into that term. So this is exact. Everything here commutes. That's clear by construction. So if I map from here to P0, and then I map to N, it's of course the same thing as this, because this thing is the same as this map, and the map into N. So this is the only non-trivial you want to check, and this one commutes. And I have this column was exact by definition, and this column is exact by construction. So now this column is exact by the 5 lemma. And moreover, and now I rotate this thing. This was constructed so that this guy is the kernel. And rotate this diagram, and let's look at the snake lemma. If you rotate this diagram, you're going to check that this co-kernel of this map is 0. So that this map is now surjective. Okay. So, all right. So now that we know that the co-kernel of this map is 0, I've gained something. I now know that I have a P. Oh, I'm sorry. Let's move on to K0 now. So now I have everything is exact in this diagram. Absolutely everything is exact. So I have K bar 0 to K prime 0 to K0 to 0. And, well, I have a map from P1, from P bar 1 to this. And this map was surjective because my original map from P1 bar to P0, this was a resolution. So the image of this map was equal to the kernel of this map. So the image of this map is actually K bar 0. So the image of this map is all of this. So this is a surjective map. And the image, same argument, the image here from P1 to K0 is all of this. So this is surjective. And of course, this continues like this. So this was exact to start with. So this was exact to start with. And that's exactly the same situation that I had before. It's just that now I have one level up. So this is going to construct me my P1 mapping here. And the composition of P1 to K prime naught, and then from K prime naught to P prime 0 is the map, from P prime 1 to P prime 0 that I want. So by induction, you continue like this, and you construct the map from P prime I to P prime I minus 1, which is a projective resolution of E. Okay, so that's the horseshoe lemma that I think I needed it before, but I never proved it. If I did, I'm sorry for proving it twice. But we'll need this now to prove that inequality here. So this is the theorem that I want to prove, which is essentially everything we're going to do today. All right, so let's start with my module M, which is again an S module, either left or right, it doesn't matter, but just in that category that you choose, pick a resolution of that. Pick a projective resolution of M. So just pick some projective resolution M, P0, P1, and so forth. These PIs into M is a projective resolution in the category of S modules. And of course, those may not be projective as R modules. Okay? But okay, so let's look at this. So let's look at M0, P0, and let's take the kernel. Shoot. 0, M, P0. Let's define K0 to be just the kernel of that. So this is an exact sequence in the category of S modules. Let's view them as R modules and just pick any resolution here in the category of R modules. But a projective resolution of M as an R module. So let's pick names for this. P. What's a good name for a projective? It should be in the category of R modules. So I'm going to use R0, R1, and so forth. So this Ri into M, this is a projective resolution in the category of R modules. Okay. And pick any resolution of K0 in the category of R modules. S is already taken, so I'll call these guys R bar, just as before. R bar 1, and this is a projective resolution in the category of R modules. So by the lemma that we just proved, there exists here a projective resolution that I'll call R prime, just as before. R prime 0, R prime 1, and so forth. But I'll remember that this actually depends on this P0, so I'll just put a 0 here. So these are two indices. Actually, let's put this index like this. 0, 0, and so forth. R prime 2, 0, and so forth. So for P0, I got a projective resolution in the category of R modules now that makes this diagram commute. And you do this for everyone. So now, so you did it for P0, and for P1 you do the same as follows. You know that the map from P1 to P0, this P was this map here, factors through the kernel of this map. So you know that you have this exact sequence now from K0, 0, P1. Now define that K1 to be the kernel of that, and repeat. So here we had this resolution R bar 0 to R bar 1. Let me rename that to recall that that was a resolution of this guy in the category of R modules. So R bar 2, 0, and so forth. So this is in the category of R modules, a resolution of K0. Choose any resolution of K1. So this is a resolution that I'm going to take is going to be R. What did I? This was 0. This is 1, 0, and so forth. And now I'm going to choose 0, 1, R bar 1, 1, R bar 1, 2, 1, and so forth. And this therefore extends to a resolution. I'm calling this R prime, 0, 1, R prime, 1, 1, and so forth. So in general, what I get is, by doing this on each one, you get resolutions R prime dot I over pi. And this is projective in the category of S modules, and this is a projective resolution in the category of R modules. Okay. So now, I claim that this is a double complex. So I claim that this thing here, if I let this guy move, this commutes. So if I look at R prime dot minus 1 I, no, the other way around, dot I minus 1, and this goes to pi minus 1, that this diagram commutes. And that's clear, right? Because the map from R prime to the one that corresponds to this guy, to this R prime here, is by looking at the map from here to here, and then you compose with the map that you get from this to this. So you get, this tells you that you have a double complex, and I needed to do something to get that double complex. Well, I get a double complex. Remember, the book does something funny, that he calls a double complex not something where everything commutes, but where they anti-commute. So you need to change the signs of every alternating column. But the point is that we have a double complex. We get a double complex R prime PQ mapping into, I'm doing this on the second one, PQ. Okay. All right, so all rows of that complex, of this complex, are exact. Except at the last column. Except at the 0th column. Right? Because the homology of this complex in the last column is this guy. This was built in such a way that this map was surjective, and it was a resolution at each one of these guys. So you just extend that double complex by that last column, and you get something that is exact. And that's exactly the same thing that we did for balancing Tor. So this tells us that the total complex of this R prime is a resolution of the module N that we started with. And this is a resolution by all projective modules. The direct sums of these guys are projective. This is a projective resolution in the category of R modules. Category of R modules. The problem is that it's just too large. It's not good enough to prove this theorem. So let's fix this resolution. Let's truncate this resolution to prove this theorem. So at some point I need to use that I can bind it. So let's do that. And I'll need a couple of lemmas. So the first lemma is this. The first observation is that this depends on M. This does not depend on M. So this is the dimension of S as an R module. Now, if the dimension of S as an R module is infinite, then there's nothing to prove. If the projective dimension of S as an R module is infinite, there's nothing to prove. And the same thing if this guy is infinite, there's nothing to prove. If the projective dimension of M as an S module is infinite, there's nothing to prove. Everything is going to be less or equal than infinite. So I may as well assume that these two numbers are finite. Okay, so let's just assume that these two guys are finite. So assume that the projective dimension of S as an R module is just n, which is finite. So this means that the original resolution that we started with, let me just assume that the projective resolution, the projective dimension of M as an S module is also finite. Let's call it M. So we could have chosen our projective resolution P dot into M to be of length M. Okay. We know that such a thing exists if it's finite, so we could have chosen this resolution to be Pm into Pm minus 1, P0, M. Okay, so claim. I can choose the arrow, the rows in this diagram. Remember that what we just constructed by that trick? The thing that we constructed were this R prime 0m, R prime 1m, and this was infinite. But the claim is that I can actually choose these guys where all rows are of length n. No. So that this double complex becomes an n plus 1 times m plus 1 complex, just because I'm starting at 0. So that's a claim, that I can choose these arrows to be of that particular length. So how do we prove that? Okay. So okay, so let's grab an S module. Okay, so the first thing to notice is the following. If you have a bunch of modules and you sum them, well, what's the projective resolution of this guy? I can choose as a projective resolution. Let's say that all of them have a finite projective dimension. So each one of these modules Mi admits a finite projective dimension. It doesn't need to be finite, doesn't matter. But the point is that how do I construct a projective resolution of this direct sum? I can just take the direct sum of all the resolutions. And that is a sum of projectives, therefore it is projective. So the projective dimension of this guy, it's bounded, because since it was the minimum length that I could take, and I'm giving you one projective resolution of that one, what is the length of that one? Well, it's you have a bunch of complexes, one for each Mi, and you take the direct sum. What is the length of that direct sum? Well, it's just the maximum length. It's just that if these are all finite, this maximum might not exist, might not be finite. So I need to say that it's the supremum of all the lengths for each one of these guys. Even though each one of these guys might be finite, the supremum might be infinite. Okay? So if I have a bunch of complexes, the direct sum, the length of the direct sum is just the supremum for the lengths of each one of the complexes. Okay, so that's the first observation. The second observation is that if I have a projective module, so if M is a projective S module, and the projective dimension of S as an R module and the projective dimension of S as an R module is whatever I chose it to be here, N, then the projective dimension of M as an R module is less or equal than N. So let's prove that. Well, if M is S itself, there's nothing to prove. If M is S itself, the projective dimension of M as an R module is N, which is less or equal than N. If M is a direct sum of S's, then this thing here tells me that the projective dimension is the supremum of N for all of N, so therefore it's N. So if M is free, this statement is true. Okay? And now a projective module is a direct summand of a free module. Therefore, this statement is still true. Okay, so if you have a projective module over an algebra that is of projective dimension as a module N, then your projective dimension of your projective module, which might not be projective, but is less or equal than N. Notice that the projective dimension of M as an S module is 0 because it's projective. Okay? But it can increase at maximum to N, which is part of this theorem. If M was projective, that's precisely what I wanted to check. So that's the theorem for the case when M is projective as an S module. So that was an easy check to check. When M is projective as an S module, the theorem is trivial. Okay, so now that means that each of these rows, I could have chosen them to be of length less or equal than N. Okay? Because the projective dimension of each one of these guys was less or equal than N. Okay, so now the total complex of this has length, therefore, M plus N. So if you have a total complex where you have M plus 1 rows and N plus 1 columns, then you're going to have M plus N plus 1 in the total complex. This is because just the diagonals are measured like this. So at some point, you're going to reach the minimum between M or N. So the length of these guys were N. So let's say that M is less than N. So at some point you reach that M, and then you continue until you reach the N. So that's M plus N that you have. So the total complex here, the length of this total complex, this became a projective resolution of length M plus N. There's M plus N plus 1 elements in this projective resolution. So that means that the projective dimension of M is less or equal than this, which is what we are choosing here. Okay. I have a little time, so I'll prove the next case, and then we'll stop. Yeah, so we have a little time, so let's prove that. So here's the one example that we want to consider is just a hypersurface inside of a space. So we have a ring, and we have a non-zero divisor. A non-zero divisor. Check if I need it to be central or not. Probably for what I'm saying, what I'm going to say, doesn't. Yeah, probably this doesn't need to be central. So that we have the following morphism of rings. So I'm just going to take the principal ideal generated by that guy. So I'm looking at a hypersurface inside of a spectrum of R. Well, if R is commutative, thinking of our commutative, but it doesn't need to be commutative for what I'm saying now. So here, this is going to be different if I take x on the left or x on the right. Nothing is going to really change. So this is going to be my algebra S. Okay, so let's take a module. Let's look at the theorem where I take a module here. M is an S module. Okay. So I want to understand what this theorem is saying in that case. Okay? So let's suppose that M is projective. Suppose that M is projective as an S module. So this means that the projective dimension of S M is equal to 0. So that's part of, so this is the first summand there, which is equal to 0. Then, how about the projective dimension of S over R? So what is the projective dimension of this guy as an R module? S as an R module. Okay? Well, M cannot be projective. M cannot be R projective. So that's kind of clear because, well, M has explicitly, it has torsion. So we know that x M is equal to 0. Okay? So we have non-trivial torsion, so we cannot be projective. Because if we were projective, we would be flat, and if we would be flat, we would not have torsion. So, in particular, S cannot be R projective. In particular, the projective dimension of S as an R module is bigger or equal than 1. So that's also true for the case M is equal to S. So this guy is at least 1. So if you have a vector bundle on a hypersurface, it's never a vector bundle on the ambient manifold. That's clear. You can multiply by a function that is 0 on the hypersurface, and you're going to get 0 everywhere. So that can never be a vector bundle on the whole space. But the question is, do you have how many vector bundles you need in the ambient space such that the co-kernel of the last map is supported at your hypersurface? So you can resolve a vector bundle on the hypersurface by honest vector bundles on the ambient space. How many do you need? Okay, so in the case that the bundle is trivial in the hypersurface, so I'm taking M to be S, this is 0, it's projective, and this is at least 1. Moreover, in the case where M is S, we know that it's exactly 1. Because OS is resolved, well, OS, I'm thinking in surfaces, but this is a resolution by free modules of S. So we just proved that the projective dimension of S needs to be at least 1, and I'm giving you a projective resolution by 1, of length 1. And so this is a free resolution of S of length 1. So the projective dimension of S as an R module is 1 in that case. So the theorem is telling us that the projective dimension of the theorem is telling us that the projective dimension of where am I? Of M as an R module is less or equal than the projective dimension of M as an S module plus the projective dimension of S as an R module that I just proven that it was 1. Okay. So if you have not a vector bundle but a coherent sheaf or a quasi-coherent sheaf on a submanifold on a hypersurface that you can resolve by n vector bundles, then you can resolve it in the ambient space by just adding at most one more. You need at most one more vector bundle on the ambient space. But the statement of the theorem that I want to state is that in this case is actually exactly equal. So theorem, this is an equal. This is equal. So you always need one extra bundle. So let's prove that. And how do we prove this? Okay, so I've checked the equality in the case where M is equal to S. So in the case where M is equal to S, so that this is 0, and I've given you the resolution as R module of length 1. So we get equality. So when M is projective, this is also true. If M is projective, I just told you that the projective dimension of, no, I just told you that the projective dimension is bigger or equal than 1. And on the other hand, it should be less or equal than 1. And the theorem is telling us that it's less or equal than 1. And I've proven that it has to be bigger or equal than 1. Therefore, they have to be equal. So when M is projective as an S module, we know that this is true. And now I need to prove it in general. So let's suppose that M, the projective dimension of M as an S module, let's suppose that is bigger than 1. Bigger or equal than 1. We know it for dimension 0, and we want to prove it for bigger or equal than 1. Okay? Okay, so we know that we need to resolve M with at least one projective. So we'll need at least one extra guy to resolve M. So let's just take the first guy. So this K here is there. It cannot be 0 to have this exact sequence, because if this sequence was exact with K is equal to 0, the projective dimension of M would be 0. Okay, so this is in S modules. All right. And P0 is projective. Is projective as an S module. So now the projective dimension of K is one less than the projective dimension of M. One less. So by induction, the theorem holds. On this number, we've already known this for M of projective dimension 0. So by induction on this number, I can assume the theorem is true. So I can assume that the projective dimension in R of K is equal to 1 plus the projective dimension in S of K. But 1 plus the projective dimension in S of K is the projective dimension on M, of M. Okay? So we may assume that for K that holds. So what are the options? So the options are that either this guy is equal to 1 plus the projective dimension of that's correct. So the options are that either the projective dimension of R once I have this condition, then I see that the projective dimension of R of M is either 1 plus the projective dimension of S on M, which is just 1 by plus this, or, so this is one option, which is good, this is what we want to prove, or the other option would be that everything is 1. Or the projective dimension of S on M is equal to the projective dimension of R of M, which is equal to 1. So it cannot be more, because by induction we're just killing everything that is bigger than 1. But it could happen that this is an equal, and we haven't proven that this is not a strict inequality. So that's the only inequality that can happen, is when this is equal to 1, and this is also equal to 1, and this is less than 1 plus 1. So this is what we want to rule out. And how do we rule out this? Okay, so this I claim either we are in the good case or this case that we want to rule it out. So I claim that this is impossible. Let's check why in the hell this is impossible. This shouldn't be hard. Yeah, so I think it goes as follows. So let's take something like this. So let's take a module that has projective dimension 1, okay, over S. So my M has projective dimension 1 over S, and it also satisfies this condition. So this is my M, and I'm going to look at a surjectum from a free module. And let's look at the kernel. This K probably is not the same as that kernel, so let's change that. Let's call this guy, I'm going to call it K. I'm not good at finding new names. So this is as our modules. Okay, I claim that and F is free. So I claim that K cannot be projective. Because if K was projective, then M would be projective, because K would be a direct summand. And the projective dimension of M as an R module is 1. Let's take the tensor product of this with our ring S. So let's tensor this with S. Since M was an S module to start with, the tensor product of M with S is just S. It's just M. But the tensor product of F with S is F tensor over R with S. Here I'm going to get K tensor over R with S. Then I'm going to get, well, the tor1 of tensoring with S. So this is going to be tor1 of M with S. And this sequence is exact. Then I'm going to get tor1 of F with S, but F is free as an R module, so therefore I'm going to get 0. So now, Okay? What is F, which is free as an R module, tensor over R with S? So this is just a bunch of copies of R. So this is just the same thing as F mod out by XF to M, which is 0. Same thing here. This is just going to be K mod out by XK, 0. And this Tor1 here and here 0. Now the interesting thing is that this thing here, this is projective as an S module. This is projective as an S module. And the question is whether or not this guy is projective or not. Okay? So now we see that the problem we're seeing here is that the projective dimension of M as an S module is 1. So I cannot have this guy being projective. On the other hand, this guy here, so this guy shouldn't be projected. But on the other hand, this guy here, what is this? We've already computed in general what is Tor1 of a module with respect to the ring itself. This S here is R mod X. So Tor1 is the set of elements in M such that is the torsion, is the X torsion. Xm is equal to 0. But this is all of M. By definition, M was an R mod XR module. Okay. So what we're saying is that since the projective dimension of this guy was 1, then, well, this guy ought to be 0, which is M, which ought to be 0. Or in other words, that was if that was a projective resolution. But remember something general, we proved that if the projective dimension, we proved the following lemma before, which is if the projective dimension of over any ring, it doesn't matter, of M, is less or equal than D, I'm going to use D, and you have a resolution like this, Pg minus 1, Pg minus 2, P0 to M 0, where all these PIs are projectives, then necessarily N is projective. We proved this last time. And here I have something that has projective dimension 1, which in particular is less than 2. So it's less or equal than 2. And I have a sequence with, actually, yes. So this is P0, this is P1, and this is N. And since the projective dimension of M is 1, this guy has to be projective. Therefore, M has to be projective. Therefore, the projective dimension of M is 0, which is absurd. Okay? So I'm taking M to be projective of projective dimension 1, and I'm checking that it has to be projective. So therefore, have projective dimension 0. So therefore, this cannot happen, and therefore, my equality was true, which is this statement that this is equal. Okay, so let's recap what the theorem says, that if I am in this situation and M is an S module, the theorem which is proved is that the projective dimension of M as an R module is 1 more than the projective dimension of M as an S module. And this is true even if these sides are both infinite. All right, I'm sorry, this time I took some time from you. Next time I'll prove the next theorem for this, and I think I'll finish with chapter 4 of this book, and then I'll move to simplicial